importance and the course contents. Now I start the conduction, convections and radiation. Incidentally, in this course, conduction and convection heat transfer, radiation will not come into picture, conduction and convection. Now between these two modes, conduction is the basic mode of heat transfer. Convection is not a independent basic mode, it is artificially conceived by us. I will tell you in detail the concept of convection heat transfer. Convection comes into picture when there is a flow. It only occurs in case of heat transfer through fluid, where the flow can take place. And because of this flow, the conduction phenomena is affected, the basic mechanism of heat transfer. So therefore, this affected convection, that is flow affected conduction, we define artificially as a different mode of heat transfer as convection, though convection is not a basic or independent mode of heat transfer. This particular thing you can write. There are certain things you must write, there are things which you may not write or may write as note, but this is very important thing. Though we tell two modes of heat transfer, conduction and convection, but basic mode of heat transfer is conduction and radiation, which is altogether governed by different physics and which is not included in this course of conduction and convection heat transfer. Now conduction is associated with a temperature difference, I already told. Whenever there is a temperature difference between 2 points in spatial coordinates, the heat is transferred because of conduction. So therefore, a temperature, continuous change of temperature comes into picture and it flows in the direction of decreasing temperature, that means in the direction of negative temperature gradient. Let us think in this way, that let us consider a direction of heat flow Q. Q is flowing in this direction and we prescribe this direction as x as a spatial coordinate. Well, and heat is flowing in this direction means there is a change of continuous change of temperature in this direction in any medium. Conduction can take place in any medium, and conduction is the basic mode of heat transfer in solid, in fluid, in static fluid, in flowing fluid, doesn't matter. All these things I will be telling in deep with concept. Now, if we have a temperature field which is a function of x only, x is a space coordinate I give in the direction of the heat flow, and if I make an ordinate t here, I can show this like this, t is a function of x. So therefore heat is flowing like this. Now if I take a cross section, a section at any distance x, at ax from the reference origin or reference frame, then what happens? Heat is flowing across this section. Now here one thing is very important, when you define the heat, we define its direction. Heat is flowing in one direction. Okay. Now why I have taken an area normal to the direction? This is because in this connection we define a quantity heat flux. Now one thing is true, that what is the amount of heat that is flowing in a direction, to know that we have to know an area over which we are interested, the heat transfer, across which the heat transfer is taking place. If the area is more heat transfer, area is less heat transfer. So an area is important. So in this regard, a heat flux is defined Qx, which is defined like this, that if the total heat transfer through an area Ax, a finite area, I prescribe a finite area Ax, is Q, then Q by Ax limit Ax tends to 0. Now it is very fundamental and basic, like the stress, that the heat transfer reduces to 0 when A reduces to 0 at a point, but their quotient attains a finite value, limiting value, and that is the heat flux, that is the amount of heat per unit area, and therefore this gets a definition at a point. That means here we have heat flux at a point. So therefore different points we have different heat flux. It may be constant, may not be constant at all points on this area. If it is constant, then simply we multiply the area with the heat flux, gets the total heat flux across the surface. But what is the difference with stress? Stress is a second order tensor. When we define stress, force per unit area, the area may be normal to the direction of force, may be along the direction of the force. But while defining the heat flux or heat transfer, it is used as a vector in a particular direction, and heat flux is defined divided by the area normal to the direction of heat flow. You understand? So heat flux is the heat transfer divided by the area. This Ax has to be normal to the direction of heat flow. So heat flux this way takes the birth. You have to know every physical quantity from its birth. Then step by step you will have concepts. Sometimes somebody starts giving the definition, conceptual definition from little step ahead. It's nothing wrong. It depends upon the circumstances. But when you teach somebody, you start from this, that this is the definition of heat flux, which is defined at a point like a stress, that is the heat flow per unit area normal to the direction of heat flow. If you this way define the heat flux, then this heat flux, for example here in the direction of x, Qx can be written by an equation, widely known, widely popular equation, and we are grateful to the great mathematicians or physicists of France. Name is Joseph Fourier, who from his experimental observation told that this will be proportional, this is a proportionality constant, to the temperature gradient in the direction of heat flow. This temperature gradient is in the direction of heat flow Qx, and a minus sign is deliberately given because the heat is flowing along the negative temperature gradient. To make the heat flux positive directions to be identified, we give a minus sign, and this is in analogy with all phenomenological equations or laws, like electrical current flows along the negative potential gradient, like mass transfer takes place along the negative concentration gradient. So therefore, to identify the positive direction of the flux, we give a minus sign so that the positive direction of the flux is associated with the negative gradient of the potential. Now the question comes here, it is a very simple case, but in practice temperature may be a function of that. That means there may be a temperature variation in this direction also. Why? If you consider this as y direction. If temperature is a function of x, not of y, if you consider this also as the y direction, then at all points temperature gradient will be same, heat flux will be same. Similarly, if it is not a function of z, at all points will be same. But in practice, temperature may be function of all the space coordinates with reference to a frame. For example, in a Cartesian frame of reference, temperature may be a function of x, y and z, and all these things today what I am telling is at a particular instant. So time also will come as an independent variable. So it may change with time. Now we are thinking of spatial variation of temperature. So at any instant, we just concentrate at any instant. So temperature may be a function of all the three space coordinates. Then in that case what happens, at any point there will be a heat flux in this direction, there will be a heat flux in this direction, and there will be a heat flux in this direction at a point. That means these are the respective heat flow per unit area normal to that direction, say limiting value as the area tends to 0. And in that case, Q is represented as a vector Qx, where I, j, k are the unit vectors along x, y, z directions with respect to a Cartesian frame. Well, Q is represented as a vector. In that case, this law given by scientist Fourier can be written in a generalized form as Q is equal to minus k grad t, that is gradient of t, where grad t is given by okay, so that Qx becomes minus k, then del t del x, because a partial notation, partial derivative has to be given. So in that case, Qx is minus k, because t is a function of and this law Q is minus k grad t, this law is known as, according to the name of the scientist, Fourier's conduction, law of heat conduction. Fourier's law of heat conduction, and this forms the foundation pillar of the conduction and the convection heat transfer. That is the Fourier laws of heat conduction, that is Q is equal to minus k grad t. Here the constant k is a property of a system and it is known as thermal conductivity. Well, this is known as thermal conductivity. So K is thermal conductivity. K is known as thermal conductivity, and for an isotropic material, K is same for all directions x, y, z. It is independent of the direction of the coordinate axis, as you know, and in that case K depends only on temperature. K depends, K is thermal conductivity, and Vt, K is thermal conductivity. It is a property, and for isotropic material it is independent of the direction of the axis, and in that case it is purely a scalar quantity, a scalar constant which is a function of temperature only for isotropic material. In this class we will discuss the things almost for isotropic materials, and this thermal conductivity in a broad sense is known as transport property relating to heat transfer. So the property which relates the transfer or flux of a quantity with the potential, with its potential causing that flux, is known as transport property, like viscosity, which relates stress with the rate of strain, diffusivity, which relates the mass transfer with the gradient of concentration. Here rate of strain is difficult at the first moment where the gradient is coming, because rate of strain is defined in terms of the gradient of velocities from the kinematics of fluid flow. Well, so therefore, this is known as, in broad sense, transport coefficient related to heat transfer, thermal conductivity. Now the unit of thermal conductivity is very simple, because heat flux divided by the temperature gradient. The thermal conductivity unit will be heat flux divided by temperature gradient. Now in SI, heat flux is defined as unit of K. Heat flux is defined as heat flow per unit area, watt per meter square. And what is temperature gradient? It is degree Celsius or Kelvin, any one of these two, divided by meter. So therefore, the unit is watt per meter degree Celsius or watt per meter Kelvin. This K is not thermal conductivity, it is Kelvin. And Kelvin unit is not written in terms of degree Kelvin, whether it is a change in the Kelvin or it is the absolute Kelvin. You understand? If you change the temperature from 460 Kelvin to 480 Kelvin, what is the change in temperature in Kelvin? 20 Kelvin, sir. And what is the temperature of the body? 460 Kelvin, not degree. Okay, so therefore it is written as Kelvin. So this is degree Celsius. So this is the unit, either this or this. Clear? Now I will time left is less. So before I finish this, I tell you this part I will extend afterwards, that the cause of thermal conductivity or thermal conductance in different material. As you saw here, the thermal conductivity is a property which allows the heat to flow. For a given temperature gradient, more is the thermal conductivity, more is the heat flux. Now this property of thermal conductivity is due to what? Is attributed to certain molecular level physics. Because any macroscopic property, whether it is a property or anything else, we define through the molecular activities. Now the cause of this thermal conductivity in case of fluids comprising liquids and gases are different from that of solids. In liquids and gases, the heat is conducted by the energy transfer between the molecules because of its collisions. Molecules are always in a state of ceaseless motions, as you know, and this motion comprises translational motion, also the rotational and vibrational motion about its own axis, and because of which all molecules have kinetic energy. When a molecule is activated to raise its temperature, its kinetic energy is actually increased. And because of random collisions between the molecules, it transfers the kinetic energy to the neighboring molecules, which gain the kinetic energy from the upstream molecules which collides with it. And there is a random collision in all directions. And because of this collision, when this kinetic energy is transferred, we conceive this as the heat transfer. So therefore, a fluid, liquid or gases having high thermal conductivity means the collisions for these molecules of these fluids at a given state property is more compared to the other. So therefore, this energy transfer due to the collision is the mode of heat conduction in liquids and gases, and conductivity arises out of that, the property. In solids, it is little different. This is because in solid, as you know, the basic difference with the liquid and gases is that in solid, the molecules are closely packed. The mean free path is extremely small and the cohesive forces are very strong. The way we have seen the viscosity effect in case of liquid and gases are different. Similar way here, it is not the collision, rather it is attributed by two phenomena. One is the flow of free electrons, another is the propagation of lattice vibrational waves. What is flow of free electrons? Flow of free electrons takes place in case of metals. In metals, the molecular arrangement is such that there are free or valence electrons, you have read in chemistry, that which form a cloud in the periphery of the atom. They are not within the atom and they share with the other atom of other element for in the reaction. This cloud of electrons is known as free or valence electrons, which are there in all metals, which take part in conducting the electrical current, flow of these free electrons from the electron cloud, and at the same time they take part in flow of enhancing the flow of heat due to conduction. So therefore, for this reason, a metal is a good conductor of both heat and electricity. And the lattice vibrational wave part is suppressed there. But there are highly ordered crystalline non-metallic substances where the lattice vibrational part becomes prominent. What is this? So in those types of solids, non-metallic solids, the molecules are arranged in an order, in an array, a set type of thing, which is known as lattice. Probably you know these things, I am not going into details of this. And there the molecules starts vibrating in a very synchronous way. As a whole, there is a lattice vibration which is propagated within the material, and that is known as lattice vibrational waves. You don't have to know much in depth of it, because this is not our course, this is for your information. And for those highly crystalline non-metallic solids, especially for, I am telling examples, diamonds, graphite, silicon, quartz, this lattice vibrational wave propagates, and that propagation makes the major contribution, not the free electrons, to the conduction of heat. And sometimes this becomes so high that these non-metallic solids exhibits more thermal conductivity than the metals, but electrical conductivity, they are very poor. They are bad electrical conductor, but good heat conductor. And that's why they are used for cooling of electronic component, and they are known as semiconductors. Now with this, I will just show some for your ranges of thermal conductivities of materials for your information. This is nothing great, you just have a look the range of thermal conductivity of the materials. This is the thermal conductivity axis, watt per meter K. This is 0.1, this is 1, this is 10, this is 100, this is 1000. And you see hydrogen, helium, air, carbon dioxide gases, they are within that range 0.1 to 0.05, like that, a little bit 0.6. Then comes the insulators, fibers, wood, then this is foam. Then comes the liquids, mercury, water, oils, they are in the range of 6, 7, 8, that is between 1 to 10, and for some oils little bit of 1. Then non-metallic solids, some oxides, rock, they lie in this range. It is the 50 to even below 1. Then the alloys, aluminium alloys, bronze, steel, nichrome, these alloys fall within this range 100, little more than 100 or below 100. Then comes pure metals. Copper is one of the very good heat conductor whose thermal conductivity is somewhere near 400, and you see those non-metallic highly ordered crystalline materials, that solids rather, that is diamond, graphite, silicon, quartz, their thermal conductivity even up to 1000 watt per meter K. They show such high thermal conductivity. Next is, this is some representative figure of thermal conductivity variations with temperature. This is for liquids. Ammonia, there is a strong decreasing trend. This is for gases. For hydrogen and helium, there is a strong increase, strong influence of temperature in increasing the thermal conductivity, whereas for air, the thermal conductivity is lessly influenced by temperature. Then it is water and carbon dioxide. Okay, next is, these are just for your understanding. For solids, you see the thermal conductivity of different solids are there. Not much of a difference. For some solids there is a sharp decreasing trend. For silver, copper, aluminium, these are very important. The influence is not very marked with the temperature, the thermal conductivity change. Okay, so these are certain information that how the thermal conductivity varies with the temperature. Okay, thank you for this class.